I'd like to discuss the application of statics to the two-dimensional case in a little bit more detail now. So in general, when we're looking at the static equilibrium of a rigid body, we know that the resultant force and moment have to equal zero. And those are the conditions of equilibrium for a rigid body. And this is with respect to any given reference point A. Now, if you think about that, that gives us two vector equations of equilibrium. The vector r equals 0 and the moment resultant vector equals 0. And if you think about it component-wise, there are 6 equilibrium equations there, scalar equilibrium equations. Now in 2D, it's a little bit simpler. If I have 2D problems, so the forces have no z components to them, and then all the forces are applied in the same plane, then what I have is that the resultant force only has 2 components to it. So saying r equals 0 gives me 2 scalar equations. If you look at the moment itself, and I calculate the moment in this special 2D case, I'll find that it only has a z component to it. So there's actually only 3 scalar component equations when I say that r equals 0 and the resultant moment equals 0. So written out in a little bit more detail, equilibrium in the special 2D case is sum of the forces equals 0 in the x direction, sum of the forces in the y direction equals 0, and sum of the moments about some reference point equals 0. So I have 3 scalar equations. And this is the way they are usually stated. Now, it turns out that this isn't the only choice that you can make. So consider a body that's supposed to be in equilibrium, and let's look at our original reference point A, but also let's look at a new point B. If I look at the moment, the sum of the moments in B, I can write that in terms of the sum of the moments in A, and then the net resultant force. Now, the moments in A are equal to 0 if I'm in equilibrium, and also I know that the sum of the forces in the x direction are also equal to 0. I'm going to leave the sum of the forces in the y direction alone for a second, because I want to determine a connection between the moments in B and the forces in the y direction. So in particular, if I take those two terms to be 0, I find that the sum of the moments in B is equal to the cross product of the vector going from B to A, so there's RBA, with the y component of the resultant. So I can come to the conclusion that the sum of the moments in B is equivalent to saying the sum of the forces in the y direction is equal to 0. And I have that connection as long as the vector RBA is not parallel to the y direction. So this gives me another way of writing the 3 equations of equilibrium in a 2D problem. So I get the sum of the forces in the x direction equals 0, the sum of the moments in A equals 0, and the sum of the moments in B equals 0. And the only thing I have to make sure is that A and B don't line up directly one above the other. And it actually turns out that there is a third option, which you can prove too. I won't go through the proof, but you can show that you can also write the equilibrium as the sum of the moments equals 0 in 3 separate points, A, B, and C. And this works as long as A, B, and C are not collinear to each other. So in other words, they don't lie on a single straight line.